Hello, everyone. Today's presentation is on Trusted Firmware M, some of the recent work we have been doing on profiles, and we are going to finish off the presentation on a demo based on Profile Small. Myself, Shibu Kriakos, I'm part of ARM's open source software group and product manager of Trusted Firmware M. Joining me in this presentation is David Wang, the TFM tech lead. We all have been hearing for a few years now there are going to be 1 trillion connected devices by 2035. And all these connected devices are getting closer and closer to our daily lives, whether it's in the form of baby monitors, health wearables, or cities trying to get smarter. And the whole coronavirus situation seems to have just accelerated the IoT deployments, whether it's in terms of remote health monitoring, drones that are used to deliver medicines and to clean our streets, or even to track the movement of important assets and people itself. However, one of the common themes that we hear with connected devices is, are they all going to be secure? Just citing here one of the IoT Business Index surveys that concluded earlier this year, which cited 45% of the respondents, especially in the enterprise space, still thought security concerns are still hampering the adoption of IoT at scale. So that just reiterates the fact that it's important to solve security in a scalable manner to achieve the dream of 1 trillion connected devices in a few years' time. This is where the Platform Security Architecture program, which offers a complete offering to build your secure connected devices, becomes very crucial. And as part of the program is the open source reference implementation Trusted Firmware M, which allows devices to adopt the project and get themselves certified either as a silicon or as an end device. So let's look at Trusted Firmware at a very high level. Trusted Firmware M provides a secure processing environment for Cortex-M devices, especially V8M trust zone enabled devices. It provides that isolation between the secure and non-secure world by leveraging the trust zone that is available on the hardware. It provides a secure boot that authenticates all the runtime images on the platform, and it also supports a set of runtime secure services, whether it's storage to confidentially store all the critical assets on your platform, or to store things like keys and certificate away from the non-secure applications and operating system. Crypto service that makes itself available through these PSA crypto APIs for doing all sorts of crypto operations, whether it's signing, signature validation, or to do TLS connection to other remote entities, and an attestation service that can be used to prove the identity of the device to a relying party like a cloud service. As TFM has evolved, we can see that there are a lot of devices now enabled with TFM as its root of trust. I'm showing a few examples here, whether it's the NXP LVC55 platform, ST's STM32L5, or the Cypress PSOC64. All these devices, either through upstream TFM support or through SDK distributions, use TFM as the root of trust and have got the relevant PSA security certification as well. At the same time, TFM is now starting to get integrated on all the popular open source RTOSes, like EmbedOS, FreeRTOS at the kernel level and at the Amazon FreeRTOS level, and with Sapphire integrating TFM for many silicon platforms. In addition to all the work we've been doing around these platforms, enablement, and RTOSes, TFM profiles is an area that we have been looking at very carefully for the last few months now. If you take the overall IoT device landscape, which is where Cortex-M and therefore TFM is targeted at, you can see there's a huge variation in the type of devices that you call IoT connected devices. It can vary from your home smart bulb or a thermometer or a slightly complex system like a asset tracker or a smart meter, or even more complex systems like a drone or a small robot or a gateway. Although all these devices do use a Cortex-M CPU, all these devices have a very huge difference in the device capabilities. So a low-end Cortex-M CPU might have limited performance. It uh, might have only a few KB of RAM and flash at its disposal, whereas a high-end Cortex-M device might have a high-end Cortex-M CPU, of course, with higher performance and with a few MB of flash at its disposal. So it's quite apparent that it's impossible to give a single configuration ready-made TFM root of trust firmware that satisfies the need of all these use cases, its security, and that can fit into these different device profiles. So this is where we have tried to categorize the overall IoT device landscape into three categories and try to define TFM profiles into these three categories, namely profile small, medium, and large. What this means is we are providing as part of the profiles a predefined list of TFM features that aligns with the typical use cases and understands the hardware constraints in each of these categories. And these TFM profiles can be used as reference profiles for application developers when they're targeting each and every use case, and they can add or remove features from these predefined list of features in each profile to match their exact security requirement for their particular use case. Now, let's briefly look at the various profiles that we've built over the last few months. Starting with profile small. As the name suggests, it is the lowest memory footprint TFM profile that we have created. It is aimed at ultra-constrained devices that runs very simple IoT applications. These are the sort of devices that wouldn't normally connect directly to a cloud service. It would normally connect to a local hub or a gateway, and the gateway would then connect to the cloud. We have a demo at the end, as I said, which shows profile small actually in use. And with profile small, it's still not a bundle of security requirement. These set of security features gives you enough functionality to meet the PSA level 1 security certification requirements. If you look at what profile small offers under the hood and compare that with the TFM diagram I was showing a few slides back, what it provides is a very simple TFM lightweight framework. It only provides one level of isolation, so it only separates the non-secure and the secure world. It doesn't support the higher levels of isolation that PSA defines. It allows buffer sharing between the normal world and the secure world. It only supports one secure context, meaning that an application can have only a single call. A second call to the secure world will have to wait till the other secure service is serviced completely. There is a secure boot, but with very basic functionality. It do have anti-rollback protection, but in terms of firmware or software update, it can only update the entire platform image in one shot rather than updating the secure and non-secure world separately. In terms of runtime services, it supports the internal trusted storage. So it supports securely storing your keys and certificates on an on-chip storage, which means the assets are not encrypted because the storage is part of the SOC itself. It doesn't offer any rollback protection, again, because it's backed by an on-chip storage. When it comes to the crypto service, it just supports symmetric ciphers, which is the typical cryptographic ciphers that you would need in such simple applications. So you would normally have something like an AES suite. You'll have SHA-256, HMAC, those sort of ciphers. You wouldn't have something like ECDSA or RSA supported as part of this cipher suite, but you can still do a pre-shared key TLS connection if you want to securely connect to your local gateways. There's the attestation service. Again, it is based on symmetric key algorithm. Again, it supports attestation, which can be used to prove your identity, but again, it is limited in terms of just supporting symmetric key-based attestation service. You'll see more about it in the demo that David is going to show in a few minutes. If you now move on to profile medium, this is again aiming at constrained devices, but slightly richer devices compared to what profile small is targeted at. These sort of devices would typically try and connect to the cloud services directly rather than going via a gateway. And this means that there should be more security inbuilt in these devices compared to a device that is aiming at profile small. Still, it provides enough functionality to meet the PSA level 2 certification requirements. And again, just like profile small, if you look at the features that is available under the hood, it supports secure boot, but again, a bit more feature rich compared to what is supported in profile small. So secure boot here still supports anti-rollback protection, but it also allows the images of the secure and the non-secure side to be updated separately, which means these devices, if they have different vendors providing the secure world and non-secure world firmware, these can be updated separately without having a dependency on each other. In terms of the framework, it is not supporting the library model. Instead, it supports the PSA firmware framework IPC model, which offers the level 1 and level 2 isolation. So it's the IPC framework that is used for inter-partition communication and for communication between the non-secure and the secure side. In terms of services, it supports the internal trusted storage for storing keys. It can also support the protected storage where you can encrypt the assets and store things in an external flash. The crypto service, it's a bit more rich. So here it supports both symmetric and asymmetric cryptography. So you have the possibility to having ECDSA, you can do signature verification, you can have AEDs type of encryption of your assets. And of course, you can use the crypto service to establish a full TLS connection to the cloud service. When it comes to the attestation service, it again allows you to prove your identity to a relying party, but here it uses the asymmetric cryptography or a public-private key pair to sign the attestation token. And finally, looking at the profile large configuration, I would say it's very much under design. So profile small and medium is now supported in TFM upstream. You can have a look at the detailed design if you go to the project. Profile large is aimed at less constrained devices. So you might have a few MB of flash and a higher end Cortex-M CPU at your disposal for achieving a more complex use case. There can be multiple vendors providing firmware to these type of devices, and it might have to cater to sort of higher attack potential, like attacks at a physical level as well. And if you quickly compare it with profile medium, this would be much more feature rich. It would have still the IPC model, but it would support the level 3 isolation, which means you can have separation between the different application root of trust services. So you can have your own custom secure services as shown as green blocks here, but without having to trust each other. It would still have the storage functionality, but it would support both protected and internal trusted storage. The crypto service with all possible ciphers and the attestation service as well. But this is under design, and you'll see more details around the design in the coming weeks in the mailing list. With that, I would like to hand over to David to talk about the profile small demo that we've put together.
Thank you, Shibu. Can you hear me?
Yes, and you can start sharing now. Stop sharing.
Can you see the slides?
Yes.
Okay. Yeah.
Yes.
Thank you. Yeah, I'm David Wang from ARM China. So I mainly focus on the TFM ecosystem enablement. So in this section, I introduce the Profile Small demo. So this is a use case of the demo. So basically, as Shabu introduced, the Profile Small just supports the symmetric cryptography. So we need to connect to the gateway instead of the cloud directly. So the gateway supports the TLS PSK, which is a symmetric based TLS connection to secure the communication between the device and the gateway. So in this example, we have 3 devices which are all ARM-V8M devices running TFM Profile Small connect to the gateway. Gateway is a Raspberry Pi 3B. So the gateway can connect to the AWS cloud based on the TLS 1.2. This is asymmetric based. Okay, so the gateway will, when the TLS PSK connection is established, the gateway will do the initial attestation check for the devices to make sure the device is in the correct secure state or life cycle or had the correct secure components. Okay, so this slide is to show the software components of this demo. So in device side, we run the TFM Profile Small in the SPE, and we mainly focus on the crypto and ITS service used by this demo. So and in the non-secure side, we run the FreeRTOS and an application to handle the TLS PSK client request, which will establish a TLS connection and forward the initial attestation request result and the following application data. The gateway on the gateway side is based on the Linux and yeah, it's a Raspberry Pi, you know, and it connects to the AWS cloud through the AWS IoT device application. So the TLS PSK server application running on the gateway is to establish the TLS PSK connection and send the initial attestation request and verify the initial attestation token, and also forward the application data to the AWS cloud through the AWS IoT device application. Okay, so this is the workflow of this demo. So the first stage is to establish a TLS PSK connection. So the key point here is we leverage the crypto and secure storage service. So the PSK, the pre-shared key, is provisioned in factory stage in the secure storage service, and in the handshake stage, the non-secure side application can use the handle of the key, but it cannot export the key to generate the session key to secure the TLS connection. And when the connection is established, the gateway will verify the device by sending the initial attestation request, and the device will ask the secure side to sign the initial attesting token and reply to the gateway. So the gateway, if a gateway is fine with the secure status life cycle of the device, then it will go to the next stage. In next stage, we create another secure partition running the sensor, running a sensor application. The sensor application is to collect the temperature and humidity data in the secure world and send it to the gateway. And the gateway will forward this data to the cloud. Okay, this is a video for the demo, which may help you better understand. Can you see the demo, the video?
Yes.
Okay, cool. Yeah, Yeah, basically this what I said. The three devices connect to the Raspberry Pi. Raspberry Pi connect to the AWS cloud. So, and here's an example of how Master-B connect to the Raspberry Pi, the gateway. So yeah, we have TFM Profile Small running in the secure side, and FreeRTOS and application running in the non-secure side. In the gateway, we run the Linux and some applications. So in the handshake stage, the device send a client hello. This is a standard TLS-PSK process. So server reply a server hello, and at this stage, we agree to use TLS-PSK, and the crypto set with this supported. And the difference from the standard TLS-PSK is that we generate the session key in the secure side. So which is that we use the PSK handle stored in the PSK stored in ITS in internal trusted storage, and non-secure side can use the handle to generate the session key. So in that case, it cannot touch the pre-shared key. So, and when the handshake finished, the application running on the device can use the session key stored in the secure side to encrypt and decrypt the message for the application data. So when the connection established, the gateway will send the initial testing challenge, and the device will sign the report, the initial testing token, and send back to the gateway. So this is the video of the demo. So yeah, this is a UART message. This is on the gateway side. We started the gateway, and the one board connected through the TLS-PSK, and this is another board connected, and they will all verify the initial testing token. So the board sends the temperature and the humidity data. So this is in AWS IoT Cloud. So yeah, the cloud can get the data. Yeah, this is a video for this demo. Okay. Okay. So basically, this is all for the demo. So do you have any questions?
There's two questions in the YouTube. I'll put them in the chat here.
Okay. Shebo, I think this question is to you. Hi, Shebo.
Can you hear me?
Yeah.
Okay, sorry, my mic was muted. Yeah, hi Eric. Yeah, multiple vendors for large profile refers to level 3 isolation, isn't it? Not entirely. So there can be a scenario where there's no level 3 isolation, but the secure and non-secure images are coming from multiple vendors. So a silicon vendor might be fully owning the secure side, and the non-secure side is completely owned by the OEM. So there also it can be a multi-vendor scenario. So there's no level 3 isolation. The silicon vendor manages the secure side, maybe just running in level 1 or level 2 isolation, and the application or the OEM always is in charge of the non-secure side. So our thinking is for low-end profile small devices, it doesn't, the systems are or use cases are going to be very simple, that one party is going to be owning the entire thing. So the secure boot just need to care about updating the image completely. So MC boot doesn't have to be enabled with multiple image feature. But when you come to profile medium, our thought process is the use cases might have multiple vendors owning secure and non-secure side. So in profile medium and large, we would enable multiple image in MC boot, whereas with a small, we would disable that just to save some code space. And as I said, it's always configurable. If someone wants profile small with multiple image update, they just need to enable a flag in MC boot. The second question on flashless MCU, I think we have had the discussions in the mailing list. It's of course possible, but to be honest, I think there is more work to be done in the current TFM over and above all the profile work to support flashless MCUs, because one of the PSA certification requirement is to have sort of rollback protected internal trusted storage. So if you don't have a on-chip storage, then you'll have to emulate that functionality in an external flash with some sort of rollback protection, maybe using some sort of OTB fuses or some sort of NV counters internally in the system, which is not supported today. So maybe we can, of course, add it in the roadmap, and maybe as a community, we can solve such a use case. I know there are certain devices which don't have on-chip storage, and this is something we need to address, but it's more work, I think, in the future roadmap. Yeah, but I think ITS is required as per the security certification requirement, but it has to be emulated on an external flash through some sort of rollback protection.